outliers that we won't use. If they find the interquartile range, if it's so many outside the interquartile range, then we throw it out because it skews your data because you're subtracting and multiplying. And we know outliers also affect the average, right? It affects the mean. It does not affect the median as much. It doesn't affect the mode, but it definitely affects the mean. So you can see this one right here. So this shows a really strong correlation, but you know, if you draw a line through here, these values are all not close. And that's probably where that line would go. Those values are not very close. So if you cut that out, it might change the correlation and not be quite so high. And this one, I think you have a really extreme low here. That one's pretty hard to tell at all. That's a really low correlation. Review. It's not a percent. It's not a proportion. Okay. So squared correlation, R squared, it's called the coefficient of determination. So R is the correlation coefficient. R squared, which is R times R, is called coefficient of determination. And based on how you calculate R squared tells you how much of the data is shared. It's kind of like a confidence interval. But to calculate, you just take R times R, or you read it off of the spreadsheet that we set up. And so if somebody gives you R squared, you're taking the square root to get back to R. This is a full-on definition of it. It's the shared variability. So the higher R squared, the more the variability is shared, the better the shared variability. The thing you have to remember is that when you square a decimal, something smaller than 1, it gets smaller, right? So 0.8 squared is 0.64. And so these R squared values are going to be smaller than the R. We have a table for them to interpret that. And I don't know what page this was in your book, but if you don't know which page that is, if you just make sure you kind of highlight that table. So when somebody asks you strength of correlation from correlation coefficient, you can use this table. Okay? How strong is the correlation? And it probably will say use table 15.1. The thing that is interesting, and this is the R value, they're saying in social studies, like in the social research, the behavioral sciences, they call this a large correlation because they hardly are able to show. They said rarely is it higher than 0.5. In most settings, not to try to get you guys confused with this, most settings, non-social science settings, is something to this effect. Okay, and so we will talk about determination here in a second. I gave you that already, right? Yeah. Okay. Is that fast enough? All right. And I have hypothesis testing up here. All we're going to do is just look at R. Okay. We're gonna talk about R. We scrapped this last minute. Actually, my brother and I talked right before class, just because of time wise. Okay. So somebody gives you this information: women's shoe size, height. Okay, this is not from this class. So on Excel, this is what it would look like. And so a couple questions. What is N? N would be the number of sample, right? So you count the dots. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 in the sample. What is R? Well, R squared is usually what's given. There is a way to do R, but R squared is often what's given. So you take the square root of that. So take the square root. You might turn your calculator like this. You're using your phone calculator. So the square root of 0.78. So it actually gets bigger. So 0.88. Then you always got to ask yourself if it's positive or negative, because you can't, when you square something, the negative goes away. So R would be 0.88. That's a pretty strong correlation. Okay? If you notice, then this line going through here, it doesn't even hit any of the values. But all the values are pretty well equidistant. I always look at it like this way, like if this is the same distance away as this one, if this is the same below as this one is above, they kind of cancel each other out. These two are about the same, kind of cancel each other out. These two are kind of the same. So the more of them that can cancel each other out above or below that line, the higher your R value is. The better the predictability. We're not doing this whole test. I'm scrapping it out of here. Do you want me to show you how to do, can we show you an R example on Excel before I go on to the line regression? I don't know that we need to break it. We cut out the hypothesis testing. Let me show you this real quick. Okay, so I entered some, so the steps over here on this side is if you want to do the whole thing on your own, okay? We had on Moodle, there is a file that says Excel scatter plot regression. It does all this stuff for you. You just got to, just like with that t-test, you just got to put the stuff in. The only thing it doesn't change is the labels of your graph. Okay, and so I want to copy this data. I want to do shoe size and height. This is for males. Males on the left, yeah. So I'm going to copy shoe size. I didn't do all 20 of them. And then I'm going to paste. And it'll show you how it's pasting it. So if it's crazy, you can adjust it. So I'm going to copy this one then. If you don't want to copy and paste, you can type them all in, but I don't want to do that. Copy, I'm right clicking to get those on there. Okay, and so then when you copy and paste, this is going to be shoe size, height, and then if you want to mess with, and I'm going to open it up so you can see the rest of the document, but if you make them both small with these nice big monitors, you can see everything. So it bugs me when they're not centered and stuff. That 11 is not right, is it?
No.
That's left over from before.
Yeah.
Okay? Look what it does to the R value, right? So there's clearly positive correlation. We put this thing on here that takes the square root for you. Okay? Just don't be deleting that stuff because then you won't be able to get it. The fancy formula for square root, those of you that are getting interested in Excel, is SQRT, square root. So it takes the square root of whatever's in there. And so R squared 0.7081, R is 0.84. Pretty strong positive correlation. If you look on any kind of chart, I mean, either one of those, 0.84, that's really close to positive. It's very predictable. Out here, it might not be so predictable, and this still says dogs and cats. You have to change that to shoe And you can change these too if you want, but I don't really want to do that right now. So you have this data here. It's not necessarily reliable out here, and I like that Excel doesn't draw a line past that. So if you're talking about, I am going to change it now so we can see, a shoe size of 2 or a shoe size of 1/2, I don't even know if those exist. Is there an adult size of 1/2 shoe? Maybe there is. If you have an adult size of shoe of 1/2, then you're still 140 centimeters tall. It's probably not true. Okay, so we're pretty confident about what's right here, and then we're going to use this equation to predict somebody that is has a shoe size of 10.2 or 10.5 or 11. We can predict. And you say, well, I can get it from my table. Yeah, because shoe sizes are nice; they go in halves. But if you're talking about research data and it's not all nice numbers, we can use this equation to predict. Okay, so I'll show you how that would work using this equation that's Excel made here. And this is your algebra lesson for the day. People need to get out their antacid now, right? So all you have to do is make sure you know what you're trying to find. Okay? So my y-axis on this one is height. Ooh, that's going to be funky right there. Taking up and down. Ooh. So my y-axis is height. So this represents height, and my x is the shoe size. So I can use this if I want to say, given a certain shoe size, how tall will the person be, I can use this equation to calculate. So we have to pick something in here. I was going to see if there's any size that wasn't included in there. No 10s, right? There's a 10.5. We say, okay, there's no 10s here. Let's figure out someone that has size 10s. How tall will they be? So you take out the x and you put in a 10. This is multiplication when there's no sign there. We'll calculate that out. 10 times, so that's about 53.3, right? Move that over once. You can calculate it if you don't believe me. So 53.3 plus, so that's like 174-ish, somewhere in there. I mean, you could get the exact number. So if you went over to your table and say, okay, here's 10, I go up to it. Sorry, 174. If I go to 10, should be right in that area. Okay? So pick another one. Let's do another shoe size. Pick. Well, is there another one that's not on there? 12. 12? Well, let's plug in 12 and see if it gives us what it's supposed to. Let's plug in 12. Because there's two 12s and they both have different heights. So what should a size 12 person be? Multiply this. What do you get?
184.85.
Oh, you already added them together?
Sorry.
Okay. So if you went to this graph, and that's about 184, right? Because there's 190 right there. And you see right here on this graph, you can see our two 12s that are on there. The one person had above average height according to our data. The one person had below average height according to our data. This would be one that'd be really nice to have a lot more data, or have the height's one that you can usually find a population mean. Okay? So that's how the prediction line works. Now I'm going to give you I want to know, this is where you got to figure out. I want to know if someone is 184 centimeters tall What size shoes should they probably wear? See if you can figure that one out. So you can get an idea by looking at the chart going over and down. But how, this is where the algebra comes in.
What's their shoe size?
What's their shoe size?
11.5-ish.
11.5-ish. How'd you get that?
I took 184, took away the plus, which is 120.89, and then divided by 5.
So you subtracted it. So an equation is like a balance, right? If this is essentially it's 121, 120.89. If you take that away from this side, you have to take away from this side, or it goes. Okay. So there you go. So if you subtract this from both sides, now you have 5.307x equals 63.11. Then you divide by that. So you're going reverse process. Divide by. You always do the opposite when you're solving an equation.
But I used 5.33 to divide by, not 5.33 cents.
That's fine. So you get about, what did you say it was? About
11.8.
11.8. And so you see if that makes sense. So if we are 184, 11.8. Okay? That's close to what our example was before. So that in size 11.8, please. So the thing I want you to understand is if you have that regression equation, use that to make any kind of predictions. Don't go back to your table and go, oh, well, if you're 11.5, then you're 188. Because this is 11.5, 188. This is 11.5, 170. I met a guy once that wore size 16s. He was 5'7".
Oh,
hands were like this big. They're like giant club hands. They hung down to his knees. Okay? I mean, giant feet. I mean, it was a sight to see. His name was Hibby. Hibby. I'm sure when he shopped for clothing, it was quite interesting. Okay, so let me go back through that. Just make sure that you understand how to use, when we get to the lab later on, that you'll be able to do this. You're going to have your data entered in the spreadsheet, okay? And whatever you want to compare, whatever two values you want to compare, you're going to highlight that column and copy it, right-click and copy, and then take it over to the calculator one and paste it. If you don't want to use two spreadsheets, then you got to go through these steps here. This will take you start to finish of how to modify the chart and everything. We kind of skipped that in the process because of time. Okay? What you're gonna, because your homework is gonna have one of these charts, and it's not gonna be men's shoe size and height. It could be anything else. It can't be the one we just did. Okay? So you can pick height and length of middle finger. You can pick shoe size, length of middle finger. You can pick female shoe size, height. I'm not sure how you would compare female's height and male's height because you're not really predicting anything. It's going to be a graph of their heights. Okay, so you want to pick two out of the three in one of each of those, or one of either of those categories. Okay, and when you go to take the information, this would be a good one to use your snipping tool. Get this stuff changed, snip the whole thing. Okay. When you get your R value on there, you can just enter this week is a Word document assignment again, so you can just type in the answers for R and R squared. But snip that whole thing. Okay? All right, so we kind of talked about regression already, okay? I was showing you that with the line, that is regression. And so the regression analysis is actually getting us the line. So when there's a trend line, that information that you get is the line of regression, called the least squares regression. Okay, let's do these to see if you got it figured out. So here's an equation. Excel gives you the equation. Excel is not going to do the calculations for you though. Well, it can, but you have to do a formula. So predict a height based on those shoe sizes, calculating those out. So I would, if everybody pushes the button in their calculator, I feel more confident that you know what you're doing here. So you have 4 answers you should end up with. Thinking about, okay, the bigger number better give me a bigger answer. Okay, so first one, 1.2413 times 10.5 plus 55.465. So it's easier when you know this side of the equation. You don't have to solve across. What was that? What did that number end up being?
70.3.
70.
You got 68.
68.
Got it wrong? That's what I was. 2413.
Did you use a phone calculator?
No.
Did you use 10.5?
I don't know what I used because now I'm getting a different answer.
What did you guys say? 68 something?
68.49.
Okay, so we can round somewhere though, right?
Plus.
Now, those of you that are using a calculator, I showed some people this. If you have a graphing calculator that you either like beat up your kids and took it from them or something, most calculators, even scientific ones, if you hit second enter, it'll bring the same equation back up, and you can just change that value if you're doing a whole bunch of calculations. Or you can just type it in again. But when you're doing a whole bunch of the same calculations, if you hit second enter, it'll bring it back up. I'll put these up here. Let's check them and make sure we get them right. So the calculator will do order of operations correctly if you just enter it like that. Division and subtraction are where things become a little bit shaky, like the screen. Easy way to check at the end is biggest shoe size should be the biggest height. If it's not, calculation error somewhere. So the correlation is the relationship. It tells us strong positive, strong negative, weak, whatever. It's a relationship between the variables. When you square that, you get the coefficient of determination. It gets rid of the sign, and it kind of tells you how much of the data is shared by that regression. And then when you get a regression line, that's our predictor. And it's good in between, it's bad outside. So let's just for fun, because it's super fun to predict. Let's see, somebody has size 17 shoes. Put 17's in right there. And Hibby's got big shoes. He might have had 17. I've known a couple people that have had shoes that big. Both of them were over 6'8". But I'm sure there's somebody that's not. What does that end up being?
76.6.
So, I forget if the original was inches, right? So that 72 inches is 6 foot, so that's 6'4½"-ish. This is women. Okay? So there are women that are 6'4½", right? I have met some of those.
They're called Tomkins.
But probably not the predictor out here. I mean, we can't, it's extrapolation, it's outside of our data. And if we said someone had, size 2 using our line, then, we don't say they're dainty feet, they're dainty, super, super short. So we have to use predictions within our pole value. So that extrapolation we got to be careful about. Okay. We talked about this one a little bit earlier. It is possible for the regression equation to place none of the actual data points on the regression line. The one point that will always be on that line, this is a little information, is that if you take the average of the x value, if you take the average, like we're doing shoe size and height, you take the average of the shoe size and the average of the height and make that a point. That will be on it. That's guaranteed to be on there. The other ones don't necessarily have to be there, but that may not be one of your data values. This one's a little bit tricky, okay? So remember that R is the relationship, okay? But the shared variance is R squared. So if you square 0.58, it's about 0.6. If you square that, you get 0.36. So it is about a third. Okay? We're not setting you up to try to trick you with true false questions about R. This is just a little check that came with it.
Is the R squared is the true predictor of percentages then?
It's a predictor of the probability